Hello everyone. Welcome back to my YouTube channel Chemical Adda. In this video, we are going to understand one of the important topics from chemical engineering, thermodynamics. The TV diagram for a pure substance, which is also known as the temperature versus specific volume diagram. So in this video, we will understand how a pure substance behaves when heated, using a temperature versus specific volume diagram. So, let's get started. So first, let us understand what a TV diagram is. So, a TV diagram, which stands for temperature volume diagram, is a graph that shows the relationship between temperature and specific volume. There are two figures representing the temperature volume diagram, where figure A shows heating of a pure substance at constant pressure, and figure B shows heating of a pure substance at various constant pressure, such as P1, P2, and P3, where P3 is greater than P2 and P2 is greater than P1. Then, in both diagrams, the x-axis represents specific volume, V, and the y-axis represents temperature, T. Therefore, from both figure of TV diagram, we can understand how a pure substance behaves when heated or cooled, especially during phase changes, like melting or boiling. Now, let's understand these two figures of TV diagram in detail. So, first let's understand figure A of the TV diagram, which shows heating of a pure substance at constant pressure. For that, let's consider a solid substance at a given temperature. So, when energy is transferred as heat to the solid substance at constant pressure, the solid expands, and the specific volume of the solid increases with an increase in temperature. So during this heating, the specific volume of the solid increases with an increase in temperature, and hence the path followed by the system during this heating is represented by line 1 to 2. Now, if the heating continues, the solid reaches state 2, where the solid starts melting. And at this stage, the system contains two phases, solid and liquid, which means that at state 2, solid and liquid coexist, and both are in equilibrium with each other. Next, if we keep the heating continued, more and more of the solid phase converts into the liquid phase, but during this phase change, the temperature of the system remains constant. And this phase change, from solid to liquid, is shown by the horizontal line 2 to 3. So during this path 2 to 3, phase changes occur from solid and liquid, and hence energy is absorbed to convert the solid into liquid at the same temperature. Hence, the amount of energy absorbed by unit mass of the substance for the complete conversion from solid phase to liquid phase at the same temperature is called the latent heat or enthalpy of fusion. Then, after all the solid has melted, further heating increases both the temperature and specific volume of the liquid until it reaches state 4. This path is represented by lines 3 to 4, which represent the heating of a pure liquid. Then, at state 4, the liquid begins to boil, and this is the start of the vaporization process. Next, if heating is continued, more and more of the liquid phase converts into the vapor phase, but the temperature remains the same during this phase change. This is represented by the horizontal line from 4 to 5. So during this path 4 to 5, phase changes occur from liquid and vapor, and hence energy is required for the conversion from liquid phase to vapor phase. Hence, the quantity of energy required per unit mass of the substance for the transition from liquid to vapor at the same temperature is called the latent heat or enthalpy of vaporization. Then, further heating, the system reaches state 5, where all the liquid has vaporized, and the substance is converted entirely into vapor form. Now, if we continue heating at constant pressure, both the temperature and specific volume of the vapor increase. And this is shown by the curve from 5 to 6. So, that's how a pure substance behaves when heated at constant pressure, which we have understood with the help of figure A. Now, let's move on to figure B of the TV diagram. This figure B shows what happens when the same procedure is repeated like figure A at several different constant pressures. So, if similar procedure like figure A are repeated at different pressures, we get multiple constant pressure lines, just like the ones shown in figure B. In this figure, you'll see three different constant pressure curves, where the pressure levels are labeled as P1, P2, and P3. where P3 is greater than P2 and P2 is greater than P1. So, each of these lines shows how a pure substance behaves when it's heated at a specific constant pressure. So let's understand this in detail. So, in figure B, in the regions marked S, L, and V, only one phase, that is, solid, liquid, or vapor, is present. Then, in the region marked S plus L, both solid and liquid phases coexist in equilibrium, and, in the region marked L plus V, the liquid and vapor phases coexist in equilibrium. Then along the line marked triple line, all three phases, solid, liquid, and vapor, coexist in equilibrium. Then, along the path 2 to 3, a phase transition from solid to liquid occurs. And, along the path 4 to 5, a phase transition from liquid to vapor occurs. Next, the states 2, 3, 4, and 5 represent the saturated states where the phase transition either begins or ends. Then, the curve AC represents the saturated liquid line, and the curve BC represents the saturated vapor line. Such that, a point on curve AC represents the substance is in the liquid state, at its boiling point, and at the specified pressure, and such a liquid is called a saturated liquid. Similarly, a point on curve BC represents the substance is in the vapor state, at its condensation point, and such a vapor is called saturated vapor. Similar condition can be observed in figure A, during the phase transition, which is represented by line 2 to 3 and 4 to 5, where the temperature as well as the pressure of the system remain constant. Hence, at a specified pressure, the temperature at which the phase transition from liquid to vapor takes place is called the saturation temperature. Therefore, in figure B, the saturation temperature, corresponding to the pressure P1, is T1. And then, the pressure at which the phase transition from liquid to vapor occurs, at a specified temperature, is called the saturation pressure. And hence from the figure B we can conclude that, at temperature T1, the saturation pressure is P1. Then, at any intermediate point like the system at state M, having the overall specific volume of Vm, is a mixture of saturated liquid at state 4, with specific volume Vf, and a saturated vapor at state 5, with specific volume Vg. So, that's all for TV diagram, where we explored how pure substance behaves when heated at constant pressure. Then, we learned about triple line, latent heat of fusion, latent heat of vaporization, saturation temperature and saturation pressure. So, don't forget to like, share, and subscribe for more chemical engineering content. And also, feel free to comment below for more content suggestions. Stay tuned for more amazing topics, and I'll see you in the next video.